This video is about graphing parametric equations, eliminating the parameter, and writing the equations of graphs in parametric form. What are parametric equations? They're another way that we can represent curves on a plane where x and y are defined by parameters. Most commonly, we use the letter t. They're particularly useful in describing movement along a curve. So, for example, we may see parametric equations written as x equals t squared plus t, y equals 2t minus 1, or something along those lines, where we have t represented from a certain number to another number. And so the parameter is often called t, that's the independent variable, and by restricting the values of the parameter, we can parameterize a specific part of the graph of a function. So we're going to see that quite often here. If we graph each set of parametric equations on the given interval, I've already made the table of values, and those aren't very hard. You just substitute values of t in order to get points. And then what we can see here is if we try to graph these things, we see that if we start at -1 and go to 4, my graph would be moving in this direction. And so what you'll see is the graph starts here and then moves up and to the right. We have x equals t squared and y equals t plus 2 from -2 to 2. So this looks like a sideways parabola where it's starting at 4, 0, and then moves this way, then moves back up. One thing you'll notice as you see the Desmos showing up is that sometimes, like in problem 1, the graph moves at a constant speed all the way from start to finish. Whereas in a problem like number 2, notice that the graph, when it starts here, gets slower as it moves toward the vertex and then faster as it bounces away from the vertex. So it's important to keep in mind that sometimes graphs go faster or slower, can go in different directions based on how you parameterize things. So if we have two more problems like numbers 3 and 4, as you see here, if we have y or x equals 1/2 t squared and y equals t plus 2 from 0 to 3, we can graph this, and what you'll see is it starts here and moves up and to the right, and the speed is increasing as we move along. For this robot problem, something similar is happening. It's starting down in quadrant 4 and then moves up through quadrant 1 and into quadrant 2, just based on substituting in these certain values for t from 0 to 3. And as you substitute those values in, you see that it moves faster and faster, and the distance traveled in the position goes further away faster because clearly the t is being squared for the x, so it's moving at a faster rate in the x direction. Now, part 2, eliminating the parameter. So what you can see is you can graph this parametric equation very similarly, both problem 1 and problem 2. You can graph them very similarly as we did to the things in part 1. But what we want to be able to do is we want to understand how to eliminate the parameter. So what we need to do is essentially kind of solve a system of equations by substitution to get rid of the t. So if I take number 1 and I look at this situation, I can say something like t equals y over 2. So I just divide by 2. And then what happens is I can take this and make a substitution in for t. So if I make that substitution, I have x equals 1/2 y, or y over 2, minus 2. And if I wanted, I can solve this for y just to get it in slope-intercept form, because a lot of us like that better. So if I add 2 over and multiply by 2, I get y equals 2x plus 4. And notice that's the graph that's being graphed. It is a line, y equals 2x plus 4. The difference is when we're in parametric equations, we're starting and ending at a certain spot and it travels in a certain direction. So there's a directional component and some starting and stopping based on the parameters, but it's going to mimic the line y equals 2x plus 4. Similarly, for number 2, I can take, if I want to solve for t, I can take this x component, say t equals x minus 2, and then make that substitution in here. So y equals x minus 2 squared. I don't need anything else. So y equals x minus 2 squared. And notice that this is exactly the parabola that's being graphed. Y equals x minus 2, the quantity squared. It's just we're only graphing it from -2 to 2 on the t values, which means my domain of this function in the x's is going to be from 0 to 4, which you also notice over here. Again, notice that when we saw the Desmos graphing of it, we saw that the speed of the line was unchanged, but the speed of the parabola was getting slower and then faster. Number 3, if I want to eliminate the parameter, I'll probably solve for t in this one. So t equals 1/2 x. And then I'll take that and replace the t here. So y equals the absolute value of 1/2 x minus 1. And as we saw earlier in the year, that would look like a horizontal stretch and a horizontal shift of the graph y equals absolute value of x, which you'll see here. So it is being graphed from t equals -1 to 2. We can also eliminate the parameter in number 4. It's probably easiest to eliminate it in the x variable again, because you probably don't want to be taking cubed roots. So t equals x minus 2. Then you make that substitution in here. Y equals 1/2 x minus 2, quantity squared, not squared, that is wrong, the quantity cubed. And so that is the graph that we're graphing. Y equals 1/2 x minus 2, the quantity cubed. That is a vertical shrink and a horizontal stretch of 2 on the graph y equals x cubed. You also probably noticed the speed at which the graph changed, which again makes sense based on how that looks. Part 3, writing your own equations. So we'll take a look at this problem, and we're going to do it about 4 or 5 times. So I can take these endpoints and just stick -6 and 4 in these spots, 1 and 6 in these spots, since those are the endpoints. Then just figure out about how much things are going up every time in order to fill all the spots. So notice that the x's are going up 2 and the y's are going up 1. So that's a pretty easy way to get equations here. So I can end up with x equals 2t minus 6 and y equals t plus 1. And as you can see here and on the Desmos representation, the graph moves up and to the right, and it moves at a constant rate. But that's not the only way that you can do that. You can make this graph move down and to the left by flipping where the x and y start and end points are. So if I just put the 4, 6 up on top and the -6, 1 on bottom and flipped where all of these points were, it's now going in the exact opposite direction with the same speed. So notice that these are going down 2 instead of up 2. And these are going down 1 instead of up 1. And so then you just have to change your parameters and realize where you're starting. So notice that on this one, we started at -6, 1. Here we're starting at 4, 6. So that makes a big difference in terms of how we write the parameterizations. Now, what if I get rid of this rule that I have to have t between 0 and 5? I can write this in an infinite number of ways. So I could just take this equation, y equals 1/2 x plus 4, which we see pretty clearly by looking at the graph. And I can change this so that I can just replace x with t. That's probably the easiest way to make a parameterization, is replace one of the variables with t and then see what happens. So if this becomes t, then y is just 1/2 t plus 4. And that's going to make my t values very different. So my t values would start at -6 and go up to 4. So notice what's going to happen here is that it's still going at a constant rate, but it's going to take 10 units of time to get from start to finish instead of 5 units of time to get from start to finish. So essentially what happens is, if I do this, it makes the graph go slower by a factor of 2. I could also replace, I could maybe change this to x equals 2y minus 8, change y to be t squared, and then x to be 2t squared minus 8. So see that I just replaced y with t squared, and then that's what y becomes. Then notice that it's a very short period of time to get from start to finish, starting at time 1 and ending at time square root of 6. So this is less than 2 units of time. So it's a lot shorter than it was before. But also notice that it's not going at the same rate anymore. So it starts moving faster as we move from left to right, bottom to top. So the graph starts moving at a faster rate as we go along using this parameterization. But let's say instead of t squared and t squared in these places, I put the square root of t. Notice if I replace y with the square root of t, I can just replace the y in this equation with square root of t. If I do that, well, now my t units are 35 units in length. So from 1 to 36. So this is going to take a very, very long time to complete. And also notice that it gets much slower as time goes on. So this first period of this first trek only takes 3 seconds or whatever the unit of time is. But when I get to the end, it's 11 seconds or 11 units of time. It just takes much longer as we move forward. So this graph starts moving slower. The parameterization changes speeds in a much slower way as time moves on. So there are an infinite number of ways to parameterize the line segment that we just did. I showed you 5 or so, but it can be parameterized going up or going down, going left or right. It can be traced fast or slow. It can change speeds. You can go fast, slow. You can go from fast to slow, slow to fast. It can even repeat over itself if you're creative, if you use some absolute values or squareds in different ways. Finally, let's go over the last things. Write a set of parametric equations to model the graph of y equals x squared plus 5 on this domain. So the easiest way to do that is to just make x equal t, which would make y equal t squared plus 5. And then you figure out what t values are going to make this work. Finally, we're going to write 2 different sets of parametric equations to model the graph y equals x to the 6th. So the easiest one is replacing x with t. Then you can replace y with t to the 6th. And that just goes from 0 to 2 for t. That would give you x from 0 to 2. But you could also make x equal to t squared, which would make y equal to t squared to the 6th, which is t to the 12th. And then that would make your parameterization values go a lot faster. So it's going to get to the same spot by the time you get to square root of 2 instead of regular 2. You could also change where you start. So if you wanted to go from -1 to 1, you could do t plus 1, and then that replaces this x with t plus 1 to the 6th. This goes at the same speed as this one, and it goes over the same spots. It just changes the t value that you start at. There are a lot of different ways that you can do this to go, again, faster or slower, or you can even do it in situations where it starts slow and goes fast, or vice versa.